It's late September 1964 in the Scottish Highlands. A young physicist named Peter Higgs is hiking alone in the rugged Cairngorm Mountains. The air is crisp, the landscape wild, and Higgs' mind is far away from his classroom at the University of Edinburgh. As he wanders among the heather and stone, a powerful idea hits him, one that will change physics forever. Hi there, I'm Gabrielle Burchak. Welcome to Math, Science, History. The story goes that during this solitary walk, Higgs came up with the idea of a new particle, a missing piece that explains how other particles get their mass. This quiet moment in the hills would eventually lead to what we now call the Higgs boson and the Higgs field, cornerstones of modern physics. But why was this idea such a big deal? To understand, we need to first look at the mystery that had been troubling physicists for years. In the early 1960s, physics was undergoing a revolution. Scientists were pulling together pieces of a theory we now know as the Standard Model, a framework that explains how the basic building blocks of the universe interact. A key idea in this theory was symmetry, the notion that certain physical processes look the same even when you change the setup slightly, like rotating a shape or swapping two particles. To explain symmetry, imagine you're building with Legos. Maybe you're making a little spaceship or a castle. Now, think about this. If you split your Lego build down the middle, would both sides look the same? That is symmetry in action. For example, if you build a Lego tower where the left side has a red brick and blue brick and a yellow brick, and the other side has the same red, blue, and yellow stacked in the same order, that's mirror symmetry. It's like a reflection across the middle. Or imagine making a Lego wheel with spokes. No matter how you spin it, it looks the same from every angle. That's called rotational symmetry, like turning a snowflake or a pizza and having it still look the same. In physics, symmetry works a bit like that. The laws of nature often stay the same when you flip, rotate, or shift something. Just like your Lego model can look the same even when turned or reflected. But sometimes small changes break the symmetry. Like if you remove a brick on one side, suddenly your model is unbalanced. That's called symmetry breaking. And in physics, it helps explain why things like particles have mass. So, back to symmetry and Peter Higgs. This symmetry helped explain how forces like electromagnetism and the weak nuclear force worked. The weak nuclear force is the one that's responsible for radioactive decay. The weak nuclear force is one of nature's 4 fundamental forces, responsible for processes like radioactive decay. Physicists discovered that, at a deep level, the weak force and electromagnetism are actually linked by a kind of symmetry, meaning they behave like two sides of the same coin, especially under extreme conditions like those just after the Big Bang. But there was a major problem. The theory suggested that none of these particles should have mass, yet clearly, many particles in nature do. Specifically, the particles responsible for the weak force, called the W and Z bosons, were known to be heavy, while the particle of light, the photon, had no mass. If the math said W and Z bosons couldn't have mass, then how did they end up so hefty in real life? And if they had no mass, some reactions would happen infinitely fast, something we never observe. Clearly, something was missing. Physicists knew they needed a mechanism to explain how particles get mass. Some scientists, like Yoichiro Nambu and Philip Anderson, proposed ideas that pointed in the right direction, drawing inspiration from how materials, like superconductors, behave. But those models didn't fully work when applied to the world of fundamental particles. By 1964, several groups were closing in on an answer. Peter Higgs, a thoughtful and humble scientist, was among them. On his Highland hike, Higgs imagined that space isn't truly empty. Instead, it's filled with an invisible field. Some particles move through this field easily and stay massless. Others interact with it, slowing down and gaining mass. Higgs realized that this process wouldn't just solve the mass mystery, it would also predict the existence of a new particle later called the Higgs boson. That one insight became his lasting contribution.
We'll be right back after a quick word from my advertisers.
Returning from his hike, Higgs rushed to put pen to paper. He wasn't the only one excited by the concept of what would soon be dubbed the Brout-Englert-Higgs mechanism, or BEH mechanism. But he was about to make a unique contribution that set his work apart. Higgs' idea, in essence, was this. Imagine an omnipresent field spread throughout the universe, later to be named the Higgs field. In the hot, primordial moments just after the Big Bang, this field would have been zero, inactive, allowing all particles to zip around masslessly. But as the universe cooled, the field's value rose, like a phase transition, kind of akin to water freezing into ice. Once the Higgs field switched on, particles moving through it would experience a kind of drag or resistance, depending on how strongly they interact with the field. This resistance manifests as mass. Particles like the W and Z bosons, which interact strongly with the field, get hefty masses. Particles like the photon, which doesn't feel this field at all, remain weightless. In other words, the field acts somewhat like an all-pervading molasses or a crowd that clings to certain particles and slows them down. To make this more intuitive, physicist David J. Miller later offered a famous cocktail party analogy. So imagine a room full of people. That's the field. A celebrity walks in, say Charlize Theron. Everybody loves her. I love her. Immediately, the crowd swarms around her, impeding her progress to move through the room. Charlize trudges along slowly, as if heavy, but an unknown person slips through the room easily, effectively massless. In this analogy, the clumping of people around Charlize is like the Higgs field, giving a particle mass. And if someone starts a rumor at one end of the room, clusters of people gather and disperse as the rumor passes. That little ripple traveling through the crowd is akin to a particle of the field itself moving through space. That ripple is the new particle predicted by the theory, the Higgs boson. What Higgs realized and what made his 1964 insight so pivotal was that introducing this field could solve the mass problem and satisfy the requirements of quantum theory, but only if one accepted a profound consequence. The theory wouldn't just have a new field, it would predict a concrete, massive particle as an excitation of that field. That massive particle is called a spin-zero boson. This was the crucial step. The Higgs mechanism gives mass to others, but in doing so demands the existence of at least one new boson. It was a make or break detail, one that would allow experimentalists to test the theory, and one that Peter Higgs uniquely emphasized at the time. In the summer of 1964, Higgs wasn't the only one working on this problem. Scientists Francois Englert and Robert Brout in Belgium and a trio of physicists in the United States, Gerald Guralnick, C. Richard Hagen, and Tom Kibble, were all developing similar ideas. Higgs wrote a short paper explaining his theory, but it was so brief that it didn't immediately grab attention. When a follow-up paper was rejected by a journal, yes, it was rejected, a Higgs paper rejected, mind-blowing, right? So when a follow-up paper was rejected by a journal, Higgs expanded it, adding the bold prediction of the new particle. This version was accepted and published, and that single sentence about a testable particle became Higgs' defining mark. The other groups also published important papers, but none explicitly predicted the new particle. That's why, decades later, the boson carries Higgs' name, a fact he has always been modest about. Over time, other scientists built on Higgs' work. By the early 1970s, physicists like Steven Weinberg and Abdus Salam used the Higgs mechanism to help develop a unified theory of electromagnetic and weak forces. At first, few noticed. But by the mid-1970s, further theoretical work showed that this approach was solid. Gradually, piece by piece, the standard model came together. One by one, predicted particles were found in experiments, except for one, the Higgs boson. To discover the Higgs boson, scientists needed to excite that Higgs field enough to shake loose a Higgs particle, a very difficult task. Because the theory did not predict exactly how heavy the Higgs boson should be, experiments had to search across a wide range of energies. Throughout the 1980s and 1990s, increasingly powerful particle accelerators were employed in the hunt. Europe's Large Electron Positron Collider, known as the LEP Collider at CERN, began running in 1989, colliding electrons and positrons at high energies to look for traces of the Higgs. It combed through many possibilities, but found no definitive sign before it shut down in 2000. In the US, the Tevatron Collider at Fermilab near Chicago, at the time the highest energy collider in the world, also searched intensively through the 1990s and the 2000s. It came tantalizingly close and even saw hints that suggested the Higgs might be within reach, but ultimately it lacked enough energy to make a conclusive discovery. The technology simply hadn't yet caught up with this brilliant theory. The torch was passed back to CERN. In the early 2000s, construction began on a new behemoth, the Large Hadron Collider, the LHC, a 27-kilometer ring buried under the French-Swiss border. This machine was designed in no small part for the express purpose of finding the Higgs boson, if it existed. Many billions of dollars and a truly global collaboration of scientists and engineers went into building the LHC and its two giant multi-purpose detectors, ATLAS and CMS. By 2010, the LHC was smashing protons together at unprecedented energies, turning energy into matter per Einstein's E equals mc squared theory, in the hopes that among the spray of new particles created in these collisions, a Higgs boson would occasionally appear and then quickly decay. It was, as Higgs himself noted, a very difficult task, like seeking a delicate signal in a roaring hurricane of particle debris. Years of painstaking data collection and analysis followed. Then, at last, came the day of revelation. On July 4th, 2012. I'll never forget this day. I saw the video. I had goose pimples then, and I still do now when I talk about it. It's so freaking exciting. Okay, July 4th, 2012, a date that has since become legendary in science. The CERN's laboratory's main auditorium was packed to the brim. Physicists, young and old, squeezed in shoulder to shoulder, some having camped overnight to secure a seat. I would have been in line days before. Okay. Peter Higgs, now an 83-year-old emeritus professor, had been invited to attend along with Francois Englert, then 79. Neither individual knew for sure what would be announced, but the tantalizing rumors had been swirling for weeks. On that big screen, live video feed connected CERN to a conference in Melbourne, so physicists across the globe could watch in real time. The atmosphere was electric. When the spokespersons of the ATLAS and the CMS experiments took the stage, the outcome was clear almost immediately. Both teams had indeed observed a new particle at around 125 gigaelectrovolts of mass with overwhelming statistical evidence. It fit the expected profile of the long-sought Higgs boson. The famous presentation slide declared 5 sigma. 5 sigma is the gold standard for discovery in physics. 5 sigma had been reached. A wave of emotion swept through the auditorium. Decades of hope, struggle, and hard work had culminated in this single moment. Peter Higgs was seen removing his glasses and wiping tears from his eyes as the audience erupted in applause. Next to him, Francois Englert was equally overcome, and amidst the celebration, Englert took a moment to pay tribute to their late colleague, Robert Brout, who had passed away in 2011 and unfortunately didn't live to see proof of the mechanism he helped conceive. It was a poignant reminder that scientific glory is often bittersweet, arriving on a timescale longer than a human lifetime. On the auditorium stage, CERN's director, General Rolf Huer, uttered the jubilant words, "I think we have it." And the crowd of physicists, normally restrained and precise, whooped and cheered like fans at a championship game.
We'll be right back after a quick word from my advertisers.
News of the Higgs boson discovery made headlines around the world that day. For the general public, the Higgs, sometimes dubbed the God particle in media parlance, much to Higgs' chagrin, suddenly became a household name. The discovery was more than just the confirmation of a single particle. It was the capstone validating the entire standard model of physics. The culmination of a 48-year quest. As one CERN physicist put it, this particle was, quote, the final piece in the puzzle that is the standard model, unquote. For Peter Higgs, personally, it meant a whirlwind of belated recognition. Within hours, he was being hailed by journalists and scientists alike. Ever the private and unassuming man, Higgs did not seek the spotlight. In fact, on the day of the announcement, he hadn't even told anyone outside a close circle why he was traveling to CERN to avoid raising expectations. He later reflected with amazement that the discovery had happened in his lifetime at all. He said, "I had no idea it would happen in my lifetime," expressing the astonishment shared by many that it took less than half a century, a blink of an eye in scientific terms, to go from speculative theory to confirmed reality. The following year, in October 2013, the ultimate accolade arrived. Peter Higgs and Francois Englert were awarded the Nobel Prize in Physics for the theoretical prediction of mechanism that explains the origin of mass of subatomic particles, the Higgs mechanism, vindicated by the discovery of the Higgs boson at the LHC. Robert Brout would surely have shared that prize had he been alive. Nobel rules don't allow for posthumous awards, unfortunately. The Nobel Committee's citation acknowledged, quote, the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles and which recently was confirmed through the discovery of the predicted fundamental particle. Unquote. In the backdrop of the Nobel ceremony, there was widespread celebration not just of Higgs and Englert, but of all the physicists, the other theorists from 1964, and the tens of thousands of experimentalists since, who together had written this chapter of science history. Higgs, with characteristic humility, insisted on mentioning the contributions of others whenever he spoke. He never considered the idea his alone, as he once noted, saying about a half a dozen people were involved in the theory at the time. But like it or not, his name had become indelibly attached to the boson that proved the point. The tale of Peter Higgs and his eponymous boson is often told as a triumph of scientific intellect, but it's also a story about the human elements of discovery, perseverance, collaboration, and even serendipity. It's intriguing that the breakthrough moment for Higgs is tied to a quiet walk in nature. In recounting the story, Higgs himself sometimes downplays the almost romantic version of the hike legend, yet he doesn't deny that stepping away from the chalkboard played a role. In fact, he has expressed that the freedom and time to think deeply and creatively were crucial for him. He said, "In today's hectic academic world, I would never have had enough time or space to formulate my own groundbreaking theory." Modern research is often fast-paced and competitive, but Higgs' experience suggests that moments of solitude and reflection can be just as important as hours in the lab. The Cairngorms hike has become emblematic of how a change of scenery or a moment of calm can spur creativity. It invites us to imagine Higgs not as a lone genius cloistered in a tower, but as a thoughtful man who literally took a hike to clear his head, and in doing so, saw the problem with fresh clarity. It's a powerful reminder of the intersection between creativity and scientific discovery. Equations and logic laid the groundwork, but insight, that almost artistic leap, came in a burst of inspiration far outside the office. Higgs' story joins the other famous eureka moments in science that occurred away from the desk, showing that science is a profoundly human pursuit, subject to intuition and flashes of insight in the unlikeliest of moments. The legacy of Peter Higgs' 1964 breakthrough is now secure in the annals of science. That one idea, forged by Higgs and concurrently by others, has enabled physicists to understand why our universe has substance, why particles have the masses they do, and ultimately why atoms, stars, planets, and people can exist. It's sobering and inspiring that Higgs' original burst of work was completed in a matter of weeks. Yet it took nearly half a century of collective effort to fully confirm it. The story illustrates how theoretical physics can leap ahead, guided by the mysterious power of mathematics, as one author put it, predicting truths about nature long before experiments catch up. It also highlights the collaborative nature of progress. Higgs' achievement was built on those before him, Nambu, Anderson, and shared with contemporaries Englert, Brout, Guralnik, Hagen, Kibble, and verified by thousands of experimentalists working at the technological frontier. Science, at its best, is a grand tapestry woven by many hands across time. So as this podcast closes, picture one last scene. In the CERN auditorium in 2012, Peter Higgs, the man who once daydreamed about mass while rambling through the Scottish hills, sits in quiet amazement as the crowd around him gives him a standing ovation. He dabs his eyes with a handkerchief, perhaps recalling the long road from that 1964 hike to this celebratory moment. Next to him, Francois Englert smiles and remembers his late friend, Robert Brout. On the screen, data plots confirm a new boson's existence. It's the culmination of a lifetime, indeed of many lifetimes worth of work. Higgs later quipped that after the announcement, a former neighbor congratulated him and his first response was, "What prize?" It was a humble and humorous reaction from a man who genuinely never sought the limelight. But there was no mistaking the significance of what happened. The Higgs boson is often called the God particle in popular culture, and it's a nickname that Higgs himself dislikes for its grandiosity. One might prefer to think of it not in theological terms, but as a testament to human curiosity and ingenuity. It symbolizes our ability to ask profound questions about the nature of reality, like where does mass come from, and to answer them through creativity, theory, and experiment. The journey from a thought on a mountainside to a discovery under a mountain, literally beneath the Alps at CERN, is an extraordinary narrative of science. It teaches us that progress sometimes requires patience measured in decades, and that even the most abstract idea can have concrete, verifiable consequences given enough persistence and collaboration. Peter Higgs' story will be told for generations, not just as an explanation of how particles get mass, but as an inspiration for how breakthroughs happen. Brilliance can emerge in quiet moments. Great ideas can gestate when one's mind is free to wander. So the next time you take a walk to clear your head, remember Peter Higgs. You might not end up discovering a new particle, but you might just find an enormous amount of clarity that changes your world. And that, in essence, is the magic at the heart of both creativity and scientific discovery. Until next time, carpe diem. Thank you for tuning in to Math Science History. If you enjoyed today's episode, please leave a quick rating and review. They really help the podcast. You can find our transcripts at mathsciencehistory.com. And while you're there, remember to click on that coffee button, because every dollar you donate supports a portion of our production costs and keeps our educational website free. Again, thank you for tuning in. And until next time, carpe diem.